This video is going to be on section 4.2, which is on the mean or expected value and standard deviation. So the expected value is often referred to as the long-term average or mean and is denoted by the Greek letter mu. This means that over the long term of doing an experiment over and over, we would expect this average. The law of large numbers states that as the number of trials in a probability experiment increases, the difference between the theoretical probability of an event and the relative frequency approaches zero. So the theoretical probability and the relative frequency get closer and closer together. So to find the expected value or long-term average mu, we're going to simply multiply each value of our random variable by its probability, and we're going to add up all those products. An expected value doesn't need to be a whole number, even if all the possible values that x takes on are whole numbers. For example, we can say the expected number of girls in 5 births is 2.5, even though 5 specific births will never give us 2.5 girls. But if we survey many couples with 5 children, we would expect that the mean number of girls would be 2.5. So we have a men's soccer team that plays soccer 0, 1, or 2 days per week, and the probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5, and the probability that they play 2 days is 0.3. We're going to find the long-term average or expected value mu of the number of days per week the men's soccer team plays soccer. So to do this problem, we're going to take our random variable x and we're going to let it be the number of days the men's soccer team plays soccer per week. It's going to take on the values 0, 1, and 2, and we're going to make a PDF table, and we're going to add this additional column, x times p of x. So if we go to Excel, we have it here under soccer part 1, and I think I might have typed these in for you. So 0, 1, and 2, and 0.2 was our probability for 0 days, 0.5 was our probability for 1 day, and 0.3 was our probability for 2 days. So now we're just going to take each value and multiply it by its probability. And once we do it for the first one, we can click on the little square and drag it down, and it will autofill that formula in. So 1 times 0.5 is 0.5, 2 times 0.3 is 0.6. Now to find the expected value, we are going to use the sum function. Nope, not the substitute function, the sum function. And we are going to add up that column, those 3 numbers. So we get an expected value of 1.1. So here's what the table looks like, and then shows the math to do what we had Excel do for us. And so the men's soccer team would, on average, expect to play soccer 1.1 days per week. So that number 1.1 is the long-term average or expected value if the men's soccer team plays soccer week after week after week. And we say that mu equals 1.1. So back to our nurse calls. So we have that sample of 50 patients. Here's what the table looks like. We're going to jump into Excel so that we can do it ourselves. So here, nurse rings. We have the different values that our random variable can take on, 0 to 5, number of calls. Here are our probabilities. Now, if you remember, and we can jump back, they were out of 50. When you type them into Excel, it likes to reduce its fractions. You can also have these as decimals. I formatted them as fractions just to show you a different way. So we're going to do the same thing. We're going to multiply the value times its probability. Click back on that, grab that little square and pull it down. And then we're going to add up, so the sum function, all of those values in that column, and we get a mu of 2.32. So what that means is that on average, a post-op patient will ring the nurse an average of 2.32 times. And up here, we just have the math. If you added all the fractions together, remember, we keep the denominator the same, we add the numerators, and when we do the division, we get the same value that Excel gives us. So if a nurse has 5 post-op patients, how many times can the nurse expect to be rung? Well, each one you would expect to ring 2.32 times. So to figure out how many times the nurse would be rung for 5 patients, you multiply those numbers together. So 5 times 2.32 is 11.6 times. So if the nurse has 5 post-op patients in a shift, that nurse can expect to be rung 11.6 times. So now we're going to do standard deviation. I'm going to see if I can, it's as small as I can make my face. So like data, probability distributions have standard deviations. And to calculate the standard deviation, we use sigma again. We're going to subtract the expected value, the mean, mu, from each data value, and we're going to square that difference. We're going to multiply each square by the probability and add the products. And that's going to give us our variance. And so we're going to take the square root of that sum for our standard deviation. We're going to look at our table for the soccer players. And we have additional columns now. If we jump over to Excel and go down to soccer part 2, you'll see we have these additional columns for x minus mu squared, and x minus mu squared times p of x. So this we've already done, but we'll just do it again real quick. Take the value, multiply it by its probability, drag that down, and then sum up those numbers to get our expected value. Now, you already had it. Maybe you just want to use the number you had. That's fine. But now for this column, you want to take each x value and subtract 1.1. If we use Excel and we drag down that and we click on the cell with the expected value and we drag it down, it's going to change it each time. So remember, I can either say 0 minus 1.1 and then drag that down. And then this one is taking 1 minus 1.1. This is taking 2 minus 1.1. The other way we can do this is instead of typing that number in, if I want to click on the cell but then not have that cell change when I drag it down, I'm going to go in here and I'm going to add those dollar signs. I'm going to say, don't change my row number here. Make this always stay C5. So now when I drag it down, you'll notice the numbers aren't going to change. They shouldn't. But if I click in here now, I'll see it's 1 minus 1.1, but it's referencing the cell instead of just typing in the number. 2 different ways you can do it, whatever you prefer. You just want to make sure you always subtract that expected value from your value that your x takes on. So now we're going to square all of those numbers in that column. So I'm going to go over, I'm going to click on it. I'm actually going to highlight the whole column. This doesn't work for all of the formulas, but it does for this one. I'm going to use a little caret, means raise it to the second power. I hit enter and it's done it for the 3 values. So now I'm going to take that column, equals the square of the difference. I'm going to multiply it by the probability. Pull that down. And then in here, this is the variance. This is the sum of that column, 0.491. My sigma, my standard deviation, is the square root. Click on this. And I get a standard deviation of 0.7007. Okay? So that's how we do it in Excel using a computation table. Here it is just one more time on the slide so you can take a look at it as we go along. How we got our expected value, our mu. Sum of the last column was 0.49 and the square root of that was 0.7. So our standard deviation for the number of times that the soccer team plays soccer per week is 0.7. Here's another example. I didn't do this one in Excel. I just did the math out, so I'll go slowly through it. But the question is, are we influenced to buy a product by an ad we saw on TV? So the National Infomercial Marketing Association determined the number of times buyers of a product watched a TV infomercial before purchasing the product. The results are shown in this table. So our top row is the number of times the buyers saw the ad. So those are the values 1 through 5. And then the percentage of buyers who bought the product after seeing the ad that many times is listed in the next row. So this is an example where you would want to double check to see that you had an actual probability distribution function. So we can treat the information in that way because each one of these percentages is a probability between 0 and 1, right? This would be 0.27, 0.31. The events up here are mutually exclusive. You can't watch an ad 2 times and 3 times. It's 2 or 3 times. And if you add up all of these probabilities, you find out that the percentages add to 100. So that would be adding the probabilities up to 1. So we can treat this as a probability distribution so we can find the expected value and the standard deviation. So the expected value mu, you would take each probability, multiply it by the data value. So 1 times 0.27 plus 2 times 0.31 plus 3 times 0.18 plus 4 times 0.09 plus 5 times 0.15. If you add those all up, you get 2.54. So I've taken 27 and turned it into a decimal and multiplied it by 1. 0.31 times 2, 0.18 times 3, 0.09 times 4, 0.15 times 5, added all those up to get this expected value mu. And now I'm going to subtract this from each of the data values. So 1 minus 2.54, 2 minus 2.54. Then we square those, add them up and square root them. And that's what it looks like in math in a formula. 1 minus 2.54 squared times the probability 0.27, et cetera, et cetera, et cetera. And we get a standard deviation of 1.67. So if we didn't have Excel, this would be what we would be looking at doing. I think Excel, it's still a lot of work. We have to do all the different steps, but it does the math for us. So we're going to do it one more time in Excel so we feel pretty confident about it. So again, we're going back to our nurse calls. So we are going to go back to Excel, our nurse rings. We have our data values. Now we have our probabilities as decimals. We're going to multiply those together. This is how we found our expected value. We already know that's 2.32. We're going to sum that column up. Hopefully we get 2.32 again. Good. And now, again, we're going to subtract our data value. Sorry, we're going to subtract the mean mu from our data value. So again, we can click on the cell and make sure we put the $sign in to hold that row solid, stable, not changing. Now we can drag that formula down. Remember, the next step is to square that column, all those differences. So we're going to go over here. We can highlight the whole thing, use the caret, raise it to the second power. I'm going to take all of those squares and multiply them by their probabilities. I'll do this one. Take that times the probability. Always be careful that you're not, skipping or picking the wrong column. And now we're going to add those all up. And that's our variance. And by square rooting our variance, we get our standard deviation of 1.224. So it is a lot of work, but Excel manages it and handles it so nicely for us. I think it makes it a lot easier than looking at that last slide about the infomercials and thinking about the math and how you'd have to do all those steps on a piece of paper. So here's that table that we just did to give us our information. So here's our expected value. Here's our variance if we needed it. And here's our standard deviation. And that is the end of the video on section 4.2. So in the video of section 4.2, when I do the standard deviation for the soccer players, soccer part 2 on the Excel sheet you can see down here. I made a mistake when I was doing this column here. So everything up to this point is fine. We did X and P of X were in there. We multiplied them together and added those up to get our expected value. Then we did each value minus the expected value, so X minus 1.1. And I did that for each column. And then this was the squared column. That was good too. But it was this column over here where instead of what I did was I took the squared difference, deviation, and I ended up multiplying it accidentally by this column, X times P of X. And the funny thing was the number you get for the sum and then for the standard deviation isn't that far off from the correct value, but I did use the wrong column. So what you want to do here is you want to take the squared difference and then multiply it by the probability. So when you do that and then you pull it down, you get the correct values. And then when you sum it up, you get 0.490. And I think that when you do it incorrectly, you get 0.491. It's just different the way these work out. And then this is going to be the square root of that. So I didn't catch it when I made the video because the numbers were so close, but these are the correct values and this is the correct procedure. So you take the squared difference and you multiply it by the probability. I hope that's helpful and I apologize for the error.